All right, so just another quick example here. This is a sort of an exercise in just using the dot convention again to derive the equivalent inductance looking into this these terminals A and B here. So basically we could replace these dotted inductors and the mutual inductance with a single equivalent inductance. And how do we do that? Well, let's go ahead and see what we can do here. Let's imagine we have a voltage source connected between A and B. We'll just call it VAB. And we're going to have this dotted inductor, of course. I'll just write it straight into the phasor domain. We're going to have a dotted inductor, of course. And then we know that that inductor is going to have some induced voltage due to the current flowing through L2. So this is J omega L1. And then we're going to have our other inductor, J omega L2, and that one's also going to have some induced voltage due to the current flowing in L1. And I'll just have to draw this a little bit lower to complete the circuit here. And let's just say that we have a current I that flows in this loop, okay? And so if I'm going to come up here and draw the I also. It's going to flow in the circuit in this direction. And so, again, to just hammer this point home, let me go grab the dot convention statement that I like to use. Okay. So I'll just paste this right here. Positive current into the dotted terminal of one coil forces positive current out of the dotted terminal of the other coil. Okay, so we have a positive current I flowing into the dotted terminal of L1. That's going to force a positive current out of the dotted terminal of L2. Okay, so it's going to force a current to flow in this direction in the circuit. Okay, and how would I force a current in that direction? Well, I would need my polarity to be plus minus so that current will flow out of that plus terminal of that source. Okay, now let's look at the other one. And of course, the size of this is going to be the current that induced it, I, multiplied by the impedance of the mutual inductance. Okay, and so here, the current that's flowing in L2 is exiting the dot, right? My current I is exiting the dot. That's going to force a current into the dot of L1. How do I force a current into the dot of L1? I need current flowing in this direction in the circuit, which is equivalent to this down here. And that means I need a plus terminal on the right-hand side to force current out of that voltage source. And this, again, is going to be a voltage-sized I times J omega M. And so now I have this equivalent circuit here, and I hope that you would agree that I can write a KVL expression for this, starting here and going this way. I'll draw my pluses and minuses here, plus, minus, and I can write VAB minus I times J omega L1 plus I times J omega M, right, that voltage source, then minus I times J omega L2, then another plus I times J omega M, and that whole thing equals 0. Okay, so you can see that I can factor an I and a J omega out of all of these expressions here, all these terms other than VAB. So I'm going to write VAB, and then I'm going to write minus I times J omega. I'll factor I times J omega out of all of these. And then I'm left with L1 minus M plus L2 minus another M, and that equals 0. And so I can basically write VAB, and I can take this entire thing over to the other side by adding to both sides. I get VAB equals I times J omega times L1 plus L2 minus 2M. Okay, and so if I were to draw a circuit that represents what I have written here in this equation, it would look like this: VAB, and then I've got some impedance here, and the impedance is J omega times L1 plus L2 minus 2M. and I have a current flowing here of I, and this is my voltage VAB. I hope that you can see how that basically represents what I have here. This right here is just an inductance, so this term right here is just an impedance that I can draw as j omega L1 plus L2 minus 2M, and my current that's flowing is just I. And so what I can basically say is that this sum slash difference of inductors here, L1 plus L2 minus 2M, forms some equivalent inductance of my original circuit. So I can say that LEQ, the equivalent inductance, is L1 plus L2 minus 2M. And so I'm basically saying that I can replace this circuit between A and B with an equivalent inductor, and the size of that inductor is L1 plus L2 minus 2M. Okay, so that's pretty much it for this problem. It's pretty straightforward, really just using the dot convention to represent the circuit such that we can write a KVL expression, and then from that KVL expression we wind up with this lump of inductances, and that lump of inductances is basically just an equivalent inductance. Okay, so I'm going to go ahead and end this video right here. If you have any questions about this, let me know. We're going to move on from this section though now, and in the next section we are going to start talking about transformers.